Hi, I'm Noam, and this is a European Symposium on Algorithms 2020 talk titled Set Cover with Delay, Clairvoyance is Not Required. And this is joint work with Yossi Azar, Ashish Chiprunkal, and Shai Kutin. So in the offline set cover problem, you are given a universe of M sets and N elements with costs to the sets. A cover is some subfamily of those sets, such that the union over all the sets covers all of the elements. The goal in the offline set cover problem is to find a cover with minimal total cost. So here in the figure, you have some universe of elements and sets, and the cover is outlined in red. In the online variant of the set cover problem, you again have a universe of sets and elements with costs to the sets, and this is given in advance to the algorithm. But then elements activate one after the other, and the algorithm must cover each element when it activates. So, for example, now this green element became active, so the algorithm chose to cover it by adding a set to the cover. Another element became active, but this element is already contained in the set that was previously added, so the algorithm doesn't have to do anything. And then another element became active and another set was added by the algorithm. The goal is to minimize the total cover, the cost of the total cover of the active elements in the end of the sequence, which is some subset, the active elements are some subset of the N elements in the universe. And you can see that this problem is it consists of some finite sequence of requests. That is, once all the elements are covered, the problem is in fact over. Another variant of the set cover problem in the online setting is the online set cover with delay problem, titled SCD. So in the SCD problem, you again have a universe of M sets and N elements with costs to the sets, but now requests arrive over a timeline rather than over a sequence. That is, before in the online set cover problem, we had elements that became active over some sequence of requests, but now they arrive over a timeline. And those requests don't have to be served immediately, but they do accumulate delay while they're pending. So now, for example, Q1, some request arrived on some element in the universe, and it is arrived at this point in time with an associated delay function D1. And now, at some future point in time, another request arrives on another element with its own delay function D2, and at some further point in time in the future, the algorithm chooses to buy the red set, thus serving both Q1 and Q2, which are pending at that time. Now note that buying a set serves all the pending requests on the elements of that set, but it does not serve future requests which are released after buying the set. Such requests have to be served by buying either a different set or the same set another time. Thus, we allow the algorithm to buy a set more than once. The total goal is to minimize the delay cost and the buying cost. So the delay cost of the requests and the buying cost of sets. And here, for example, Q3 arrives on the same element as Q2, but it arrived after the algorithm bought the red set, and thus the algorithm has to buy another set in order to serve Q3. An issue that I haven't discussed regarding the SCD problem, the online set cover with delay problem, is when does the delay become known to the algorithm? So there are two options for this. The first option is set cover with delay in the Clairvoyance setting. In this setting, the algorithm gains knowledge of the entire delay function of the request QI upon its release. So when it becomes aware of QI, it also becomes aware of its delay function DI. Another option is non-clairvoyant set cover with delay. In this setting, the algorithm only sees the delay when the delay is incurred. That is, at time t, the algorithm only knows the values of the request's delay functions up until time t, but does not know the values after time t. In fact, this more general non-clairvoyant setting, it in fact generalizes the classic online set cover problem. That is, there exists a reduction from online set cover to non-clairvoyant set cover with delay. So for the set cover with delay problem, there has been a previous result in a paper by Carrasco et al. And they presented an algorithm which is log capital N competitive, where capital N is the number of requests released. This algorithm takes exponential time as it makes oracle calls to computing the optimal offline solution of subproblems. And it is clairvoyant. That is, it requires a priori knowledge of the delay functions of the requests when they arrive. They also presented a lower bound of omega of log capital N for the set cover with delay problem, which matches their guarantee. But if we try to translate it to something that depends on the number of elements in the universe rather than the number of requests, then that only translates to log n. Our results are as follows. Denoting by k the maximum number of sets containing any specific element, we first show, for the case that where k equals 2, which is also called vertex cover with delay, a 3-competitive, deterministic, non-clairvoyant algorithm. But unfortunately, that algorithm, while it is constant competitive for the special case where k equals 2, doesn't generalize well for the general set cover with delay problem. That is, its competitive ratio is linear in k. We also present a randomized O log k log n competitive non-clairvoyant algorithm for the set cover with delay problem. And since, as I mentioned earlier, the set cover with delay problem in fact generalizes online set cover, then through a lower bound for online set cover, this is in fact optimal for non-clairvoyant algorithms. In addition, we show lower bounds for this problem of omega of square root log n and square root log k. And these, in fact, apply to randomized clairvoyant algorithms as well. That is, between results 2 and 3, we in fact show that non-clairvoyant algorithms can be quite competitive for this problem and really do approach even the best possible clairvoyant results. So in this talk, I'm going to focus on results 2 and 3. First, we start with result 2, that is the upper bound of O log k log n. And in order to show it, we're going to do this in 2 stages. The first is designing an O log k competitive algorithm for a fractional relaxation of the set cover with delay problem. And then we're going to show a rounding scheme, a randomized rounding scheme, in order to obtain the final algorithm. So in this fractional relaxation of the set cover with delay problem, instead of buying a set, the algorithm is allowed to buy fractions of a set. In order to know when a request is served, you need to look at the bought fractions of sets that contain that request. And once the sum of those fractions is at least 1, then that request is served. We're going to see an example of this in a bit. Until the point in time in which the request is served, that request accumulates some partial delay. That is, somewhere between 0 and the value of its delay function at this point in time. So we'll see that in a bit as well. But consider that this fractional version, the fractional version of the problem has also a continuous description. And in this continuous description, we in fact set a buying function. The algorithm sets a buying function at any point in time t for every set s. That buying function is denoted by xst. And this buying function is integrated upon to find the total bought fraction of that set at some interval in time. So let's make this concrete. Here's an example. We again have a universe of sets and elements, and here we have the buying functions of two of the sets in this universe, okay, the blue set and the red set. Some request Q1 is released on an element, which is in both the blue set and the red set. If we want to know what is the covered fraction of Q1 at some future point in time t, that is, which fraction of Q1 has been served by the algorithm thus far, what we need to do is integrate over the buying functions of the sets containing the element of Q1, and then sum over those. So the covered fraction of Q1 at t is the sum of the red and blue areas. As for the delay, we can see here the sum request Q1, its delay function, and its covered fraction. So the covered fraction of the request starts off as being 0 and grows toward 1 as time advances, and then at some point surpasses 1, at which point the request is considered served. And the incurred momentary delay at any point in time t is scaled by 1 minus the covered fraction. That is, at this outline point in time t prime, the covered fraction of the request is 0.7, thus its incurred delay at time t prime is scaled by 1 minus 0.7, which is 0.3. Thus, over time, the delay function of the request looks like this. The total delay incurred by the request is this gray area shown here, okay, which tapers off to 0 as the request becomes served. Now we describe the algorithm for this fractional relaxation. So for simplicity, let's assume henceforth that the cost of each set is 1, and the momentary delay of each request is also 1. This is just for describing the algorithm, not for any significant purpose. So the algorithm at any point in time looks at all the requests and all of the sets containing those requests. So for each qj in some set Si, it computes the current momentary delay of requests in Si, which were released prior to qj. This amount is denoted by dij at time t. So this is shown here in this equation. And recall that when we talk about current momentary delay of requests, we're not referring to the value of the delay function, but rather to the partial delay, that is, the value of the delay function scaled down by the covered fraction of that request. Then this amount dij is plugged into an expression xij, which is an exponential function that depends on dij, and can be seen as the demand the depending request qj places on buying the set Si. This is the equation form of this expression. Then, in order to compute the buying function of a specific set Si, the algorithm sets this buying function to be the maximum over all requests j of their demand of the set Si. So it takes a maximum over those expressions xij defined before. And this algorithm can be seen via dual fitting to be O log k competitive. Now let's provide some intuition for why, in fact, we want to use this exponential function when the sort of trivial algorithm to think of is just linear buying. That is, once when you incur delay on some element, you raise the buying of the sets containing that element proportionally to the amount of delay that you incur. So let's see a counterexample for this. So this counterexample is shown here. So you have this flower here, okay? This flower contains k-1 elements, and each element gets one request at time 0. Each element is contained in one middle set, which is shared by all of the elements, but is also contained in k-1 peripheral sets, which only contain that specific element. Now, the optimal solution for this is quite simple. Just buy the middle set at time 0 and pay a cost of 1. However, the algorithm is going to do something much worse. The algorithm for each unit invested in the middle set, k-1 units will be wasted on peripheral sets. Okay, and these peripheral sets do not contribute much to the serving of those requests. This example can easily be seen to be omega of k competitive. Now, I'm not going to go into the dual fitting proof of the fractional algorithm, but I am going to give some taste for this proof, and this taste is going to be just showing the LP formulation of the problem. So this is the LP formulation of the primal LP. So the variables here are XIT, the momentary buying of the set Si at time t, and PJT, the uncovered fraction of Qj at time t. And the goal function, as you can see, consists of two terms. The first term is the buying cost of the algorithm, and the second is the delay cost of the algorithm. So I won't dwell much on this primal LP, but for the dual LP, I would like to outline its structure. So this can be seen as you would like to maximize some portion of the possible delay cost. That is, YJT is at most 1, which is the current, the maximum current delay of Qj. And you would like to maximize some portion of those delay costs, the sum over Yj's. But you cannot charge the optimal solution a cost that it can avoid by buying a set. So what this constraint, what this blue constraint means, is that you can't charge at any time t, you can't charge a future delay after time t of requests released before time t, which are in a specific set. That is because the optimal solution can avoid that cost by buying the set at t, serving all of those requests without incurring the delay. So this total charge cannot exceed the cost of Si. This is just for some intuition on the fractional algorithm. Now, we have this black box of a competitive fractional algorithm, and we need to round it to obtain a randomized integral algorithm. So we need to show a rounding scheme. The end goal is to have a rounding scheme which loses log n over the underlying fractional algorithm, which would yield a no log n log k competitive algorithm. And we're going to obtain this in two parts. First, we're going to show a simpler log capital N log k competitive algorithm. That is a log capital N loss in the rounding, where capital N is, again, the number of requests. Then we're going to show how to modify this rounding scheme to fix this capital N and change it into small n, the number of elements. So let's start with this capital N log k, log capital N log k algorithm. So we're going to fix our fractional algorithm, and we're going to let XIT be the momentary buying of the set Si at time t in this fractional algorithm. Now, in the integral algorithm, in the randomized integral algorithm, we're going to use two types of buying of sets, that is. The first type is randomized buying, And this type of buying is going to serve each request with high probability. The second type is deterministic buying, which is going to serve as a fallback for requests which were neglected by the first step. That is, requests that were not served by the randomized buying. And the expectation is going to be that this deterministic buying doesn't happen too often, because randomized buying would take care of most requests. So let's see how this works. First, the randomized buying works by setting a threshold for each set. So the graph shown here is for a specific set Si. We're going to draw a random threshold from between 0 and 1. In fact, between 0 and 1 over 2 log capital N, since this is scaled by 2 log capital N. And once this threshold is reached in the buying of the set in the fractional algorithm, that's XIT there in the graph, once the total buying has reached that threshold, we buy the set Si in the integral algorithm, and we redraw the threshold, again from 0 to 1 over 2 log capital N. Once the threshold is reached, we again buy the set, and again redraw the threshold, and so on. And this is done for every set in the universe. And this can easily be seen to cost at most O log capital N times the buying costs of the fractional algorithm. And this log capital N comes from the scaling of the algorithm shown here. The second part, deterministic buying, states that if a pending request is half covered in the fractional algorithm at some point in time, but is not yet served in the integral algorithm, then we're going to very specifically serve this request by buying the cheapest set which contains it. Okay, so here we have a graph of the uncovered fraction in the fractional algorithm of some specific request. So it goes from 1 down to 0 as time advances. And once it reaches half, that's when deterministic buying takes place if the request has not yet been served by the first type of buying, the randomized buying. So this rounding scheme, as stated, obtains a log capital N loss over the underlying fractional algorithm, and it remains to change this to an O log small n loss. So again, recall that our goal is to obtain, our goal in doing this is to obtain something that has a competitive ratio which depends only on the universe. So small n and k, they depend on the universe, but capital N is the number of requests, which might be arbitrarily large and thus obtain a very bad competitive ratio even for a very small universe. So we would like our competitiveness to depend on the universe alone, and in modifying the rounding, as we're going to see, we're going to obtain this result. And the way to modify the rounding is by aggregating requests on the same element to gain one aggregate request. Okay, so what's going to happen is on each element at any point in time, we're going to have at most a constant number of aggregated requests, each of which consists of many original requests. Thus, we're going to have a linear number of aggregate requests overall. And it turns out that once we have this linear number, linear in n, in small n that is, we're going to be able to change the randomized amplification. Okay, instead of scaling by 2 log capital N, we can scale by 2 log small n. And this is enough to obtain the required competitive ratio. So this is how this looks. This is a graph for one specific element, and it shows the total buying of sets containing that element over time. Okay, the total momentary buying of sets containing that element. And we can see these green lines across the timeline. These are requests that are being released over time. Now we're going to cut up this graph into chunks of size 1 over 4, and each chunk is going to be one aggregate request. So all of the green lines inside the chunk are part of that single aggregate request. Now, our deterministic buying is going to happen with respect to these aggregate requests. That is, once we reach the threshold, which is 2 thresholds after the end of the request, of the aggregate request, we're going to deterministically buy the cheapest set containing the element and serve this aggregate request. So that's it for the rounding scheme. Now I'm going to talk a bit about the lower bound. So what we want to show is lower bounds that apply for any algorithm for set cover with delay. So there are some options for this. The algorithm can be either fractional or integral, and it can be either randomized or deterministic. It turns out that it's enough to show a lower bound that applies to deterministic fractional algorithms. The reasons for this are that randomization does not help fractional algorithms at all. It can be replaced with expectation deterministically. And also, the optimal solution that we're going to consider is integral. And thus, the lower bound that we show will apply also for integral algorithms. So henceforth, we're going to consider only deterministic fractional algorithms. So we're going to describe the lower bound by a collection of set cover with delay instances, II, for every integer I, any natural number I. So II is going to have 2 to the I sets and 3 to the I elements. Now, for II, we're going to show that every algorithm is omega of square root I competitive. Now, plugging in what we know about the sets and the elements, this would yield lower bounds of omega of square root log k and omega of square root log n. So now we're going to see how to describe these IIs. So first, we need to describe how their universe is constructed. So we're going to construct these IIs in a recursive fashion. So the base case is going to be I0. So that's a universe of 1 element and 1 set that contains it, which costs 1. Then, when we move from II minus 1 to II, we're going to duplicate each element 3 times. So we're going to have 3 copies for each element in II minus 1. And then we're going to have 2 copies for each set. Okay, so now we have denoting by colors the copies of each element. So each element has a red, blue, and green copies. Then each set is going to have 2 copies, a regular copy, which contains the same elements as the original set, but it only contains their red and blue copies. So this is shown here. This is shown here. And this set, in fact, costs the same as the original set. And we also have a premium copy. So that's a copy that contains the red and green copies of the elements. And it costs a bit more than the original set. So that costs 1 plus alpha I times the cost of the original set. Okay, here we can see the evolution of sets as the index of the instance grows. Okay, so note the duplication of elements and the duplication of sets. Now it remains to describe the requests of this instance. So they appear over a timeline of 3 to the I time units. Here you can also see the universe of this II instance. At time 0, we're going to release singleton requests. So these requests are released on the green copies of elements. And initially, they're not going to gather any delay, but at the last third of the timeline, they're going to start gathering delay. Then we're going to recursively release an instance of II minus 1 on the red elements. And then the algorithm has to contend with this instance, which is released in the first third of the timeline. And it can do one of 2 things. it can either use a lot of the premium copies of sets when serving the II-1. These copies contain many of the green elements, or it can avoid using these sets and instead use many regular copies of sets, which contain the blue elements. If the algorithm decides to use many of the premium sets, then at the second third of the timeline, we're going to release recursively an instance of II-1 on the green elements. Otherwise, if it decides not to work with the premium sets, then we're going to release an II-1 on the blue elements. And of course, we need to describe the base case, a single request in I0 during a timeline of 1 time unit. Now, the intuition for analyzing this lower bound is that there is a trade-off between the regular and premium copies of a set. The regular sets are cheaper than the premium sets, but the premium sets, while also serving this II-1 instance on the red elements, they also do a bit more. They serve the singleton requests, which are released at time 0. And this is the trade-off used in this construction. So to conclude, we've seen for online set cover with delay, we've seen an O log N log K competitive non-clairvoyant randomized algorithm. We've also seen lower bounds that hold even for the clairvoyant setting of omega of square root log N and square root log K. And we also saw, as a side result, an O log K competitive algorithm for the fractional problem, which is also non-clairvoyant. And we haven't discussed this in this talk, but there is also a 3-competitive deterministic non-clairvoyant algorithm for the special case where K equals 2, that is vertex cover with delay. So thank you, and hope to see you in the poster session.